Greetings. The second international conference of Pervasive Computing and Network. Uh, we have developed an article to present, and I am Charles Roberto Teles, and the co-author is Arxman Roy. Our title of work is Transmission Predictive Tool based on policy measures adopted by countries using basic statistics. Uh, we are pre-recording this video due to uh, internet and time zone problems to present it in actual time. And our work is based mainly on the specific problems of SEER model equations, where we have the SER compartments of the equation, and S the susceptible, E the infectious, and R the removed compartment. This research points to the asymptotic stability of the SEER model equation to predict the behavior of SARS-CoV-2 infection dissemination patterns over the effect of policies adopted by countries. One main problem about trying to track spreading patterns of the SARS-CoV-2 remains to confounding behavior of the infectivity around the world. And these predictive results can fail because the virus contagion within the population, the aspect of the societies in convolutive aspect can create sometimes a complex network of variables. And by removing in our research the S and R compartments of the equation, that's not a usual way of treating the problem. We can create an environment of asymptotic stability for only one compartment, that is the I compartment. And this becomes the most stable point of analysis to achieve proper predictive methods and results that can be viewed by the global solution for policies and COVID-19 reduction. Concerning the confounding scenario, we have here in this image, we have the fatality rate, the infection rate, and transmission rate. And all these points have several others features that sometimes create very problematic performance for automated tools or machine learning techniques. We have contact rate, isolation measure, location, duration of infectiveness, immune system variance, virus biology, incubation period, how long the virus survives on surface, super spreader events, susceptible population, risk in terms of environmental risks, urban spaces, the type of policies, individual compliance to the policies, and this situation, in our view, and most of the researchers trying to focus on the viral seasonality, it is pointing to a very complicated scenario if you compare to the normal influenza virus, because normal influenza generally have its properties based on winter time, and COVID-19 in several other research trying to identify the seasonality, we cannot see a very well shaped seasonality in terms of winter or other seasons. Uh, One example that we can show you now is the uncertainty of predictive models, and here during the first semester of 2020, we have uh, this shaded region in these two graphs where you have very several automated tools to identify how the virus will behave in that time for USA samples, and you have shaded regions showing the uncertainty to predict how the virus will behave. And this is very related to the previous uh, slide where you have some problems concerning the variables that sustain the event and how to get a model to best fit a predictability and sensitivity power. I have listed here some 6 points. Let me start the first one. First, the serum models and its variants failures to achieve good to fit SARS-CoV-2 infectious spread patterns over time is very observed in the previous slides. You might be asking why I didn't get the daily nowadays graph or an analysis. And one problem is that we have in this period, the 20 and 20 year, we have a very typical scenario because we don't have vaccines, we don't have perfect policies. We are in a period where governments and society were still learning about the disease. And this moment is very rich to understand the disease evolution and its spreading patterns in our view. We have here automated tool proofs that is the previous related to the previous slide showing the uncertainty and lack of fixed point orientation and asymptotic stability for SNR. We have some embedded components between policies range, individual behavior compliance, and general spreading patterns. And concerning statistics, we have some fixed point stable parameter in our research that can create a confident region of statistical analysis in terms of observation of the exponential growth of virus along days. In this research points mainly since we have removed the SNR compartments of serum model equations, we have policies adopted by countries as the most reliable form of analysis. So, we understand that predictability and sensitivity are very related to these points. And how we did the filtering process? We got the function, exponential function, and the traditional C model equation, and reduced to a more simplistic and with these patterns already of confounding patterns in the equation where the infectivity compartment is influenced by these three terms of unpredictable scale of infection, inconsistent transition rate, and unpredictable shape distribution. And these two terms of the new equation have asymptotic instabilities generated by SNR compartments. And this heteroscedasticity form for K and the other term need to be removed to achieve this condition, viable parameterization aspect and possible anormal distribution of the event. And concerning infectivity and population, here we have a modified equation where the global proposition for this method is concerning removing SNR, where I compartment can be asymptotic to eye, a new eye where the infection, spreading, and dissemination patterns are viewed under policy measures influence. And at this point, we're gonna get this region of analysis, and it is possible to reject unstable critical points generated by non-normality that are apart from the condition of viable parameterization for policies only. This region of analysis and the equation that describes our analysis here, we can get here mainly a basic statistics form of analysis. And how we projected it. We got first two main modest statistics and two main variables that we understand that can be able to predict the event very clearly. And this is what we call R equals the population, infected population, divided by the time of analysis. And we have performed this analysis, and you can see in the graph, in the table here, that for example, the worldwide, we have on 7 April an increasing pattern of infection, and during the analysis of 9 days from 7 April to 13 April, you still have a growing aspect of infection. And why this is important? If you consider this date, the first column, you have here already a possible indicator, numerical indicator of how the disease will be showing its patterns. And one important aspect of this research, and mainly the sample collected that is related to 20 and 20 year, is that the data collected during this period, as I spoke before, had no vaccines and no other technological scientific knowledge. It was all partially or not fully developed. And here we have continuing the first example analysis. If you get the 13 April and 1st May, you have here 19 days of predictive analysis where policies were modified. And when policies were modified, you have already the numerical indicator showing the difference of infectivity behavior, and so on. You have some samples of countries where we have made the analysis. For example, Brazil here is in fully growing patterns during this period, the first semester of 2020. You have some countries here that adopt some policy measures that were very, very effective, and we can list two countries, that is China and South Korea. If you analyze South Korea, you have here decreasing pattern of infection, and then it stayed stuck in the same pattern, and it didn't change. But after in 2nd June, it started to reducing a lot because the policies adopted were very, very effective. You can check here the China. It's the same pattern of observation where policies were effective. Then you don't have any instability. That's why we, in the beginning of this presentation, we pointed to asymptotic stability or instability. But here, with this method, we can mainly identify the asymptotic stability of the event. By excluding the confounding scenario that make our methods of C model, traditional model equation, very disturbed with several noises, we can get in this particular research only the policies analysis. But this research has a limitation concerning this because the research didn't specify what type of measure was adopted by a country, what type of measure is the best or not. We just identified that some countries were able to use some policy measures and obtain a very good result, while other countries during this specific period of analysis didn't use any policy measures, or it was not fully developed in the country, or citizens' adherence to these methods were not in compliance. So, this is a limitation, but also a new scope for future research because with this method you can track by day, you can use very small times of analysis or very big ones, and you can get what type of policy was the best to use during this time of analysis, what results were obtained by this numerical indicator, and this can be used to support the governments to adopt the best of the policies and technologies nowadays that we have available to fight coronavirus. And here we have some just representative of the research. Here you have in blue color and red color the asymptotic stability or instability, where confounding environment, that is the red color, you can get as the previous slides showing that very unstable regions of analysis for prediction results. And here at blue color you have the normal, apparently normal distribution only for the policies case that is sustained by this method we applied in this data. And this situation leads us to the following conclusions. A method to be used as a qualitative and numerical indicator for local or global COVID-19 epidemics dissemination patterns is offered, and it is based on daily new cases time series data. As we talked before, we have a very simple mode statistics based on two very simple variables, that is the infected population and time period of analysis. And second point of conclusion, these results obtained show that the indicator can be valid as a predictive method of analysis in terms of identifying how the epidemics are behaving over time. And this could be very visible in this graph, and it was very useful before, and it is still useful to be used worldwide, also as an automated tool. We don't develop it an automated tool to make this analysis very wide, very relevant to this specific conference, but we are still working on this project to be able to automate this method. One third point of the conclusion, the method used is highly sensitive to policies adopted by countries, having a confidence power relative to how a country responds to an epidemic in terms of these policies that were implemented by this country. And the importance of this research is about which strategic policy intervention can be proposed, done, what we learned from the previous past experience, and how we can make new predictions based on those experiences. So it's a very interesting numerical indicator. And we are fully open to contact and also critics or other implementation of the method. And here are my contacts, and also you can find my co-author Arkisman in the Google and his research in the Publons, Twitter, Facebook, ResearchGate. We have several other research for COVID-19 and seasonality mainly. I thank you very much for the opportunity to present this research, and we look forward for new very interesting research. Have a good night and all the best for you.